Hello everybody. In this video, we will go over the notebook for image classification using convolutional neural networks. In the previous notebook, we went over image classification using multi-layer perceptron. And we saw that the performance was very good, about 88%, but there are some limitations to using a multi-layer perceptron for solving image classification problems. And in this notebook, we are going to show you the right way to solve image classification problems, and it involves convolutional neural networks. Before we go into what the architecture looks like, let's look at some of the limitations of multi-layer perceptron. The first thing is that it is not translation invariant. So the model that we trained in our last notebook, if we give it this image, it will correctly identify it as a boot. However, if we translate the whole image, if we move the whole image down or up, then we will see a different classification. Now, some of this can be solved by data augmentation, but fundamentally, a multi-layer perceptron doesn't take translation into account. On the other hand, convolutional neural network, because it is based on this idea of convolutional filters, it is translation invariant and it will do a much better job on these images. The second thing is that multi-layer perceptrons have a lot of parameters because they are fully connected. Every node in the current layer is connected to every node in the next layer. So it's a very dense connection, which means that the number of parameters is very large. On the other hand, in convolutional neural networks, a lot of these weights are shared between filters, and that is why there is no blow up of parameters. So we are able to extract very useful features and keep the number of parameters low at the same time. Now let's look at how to use convolutional neural networks using Keras. Most of this code is a copy of the code in the previous section, so we can just skip over it. But briefly, we are importing the data, we are exploring the data and displaying some examples of the data, and then we are pre-processing the data so that it is normalized between 0 and 1, and the encoding is one hot encoding. Now, this is the new part where we are defining a model. Instead of a multi-layer perceptron, we are going to define a convolutional neural network. Let's go over the architecture of our convolutional neural network. We have 6 convolutional layers and 1 fully connected layer. The first 2 convolutional layers have 32 filters or kernels, and the window size is 3 by 3. The remaining convolutional layers have 64 filters. We also add a max pooling layer with a window size of 2 by 2 after each pair of convolutional layers. We add dropout layer with a dropout ratio of 0.25 after every pooling layer. The last layer is a dense layer which performs the classification among 10 classes using a softmax layer. So in code, you can see we are adding the first 2 convolutional layers which have 32 filters. Size of each filter is 3 by 3. And the activation is ReLU. Usually people use ReLU activation and it does a very reasonable job. And as we have seen in previous examples, when you define the first convolutional layer, we have to provide the input shape because this layer is connected to the input and we need to provide the input shape. And subsequent layers, we do not need to provide any input shape because it is automatically calculated from the previous layer. So we add the 32 filter layers, and then we have the max pooling layer. This downsamples the image. We have the dropout layer, which prevents overfitting, as we have seen in another example. And then we have these 64 filter layers. Each has a size of 33 by 3, and we follow it with a max pooling layer. And similarly, you can read the code here. At this point, we want to flatten the layer because the shape may not be exactly what we want. And once we flatten this thing, we add a dense layer to it, which has 512 nodes, and the activation is still ReLU, and we add a dropout here as well. Now, you may be thinking, how did we come up with this architecture? And there is no good way to say which architectures will work. It's a very trial and error process. Usually what people do is take a standard architecture and modify it for their problem. So sometimes people know that certain architectures work really well. For example, GoogleNet works very well, and you can use it for several classification problems by something called fine-tuning, which we will come to in the next few sections. So don't worry too much about how we came up with this architecture. The important thing to note is that we added a few convolutional layers, and we added a few max pooling layers to downsample the image. And we did this, and we added, for example, a dropout layer to prevent overfitting. Other than that, the exact architecture, it is a lot of trial and error. You have to see which architecture works for your problem, or you could use a standard architecture instead. I would also like to point out that there are certain things that are known to work well. Small kernels like 3x3 kernels are better. Usually if you go to 5x5 kernels, or 11x11 kernels sometimes, which was, I think, used in AlexNet, those things are very wasteful. They consume a lot of processing time, use a lot of parameters, and do not perform as well. So small kernels, 3x3, is usually used, and the activation is usually ReLU. It does a very reasonable job. So those are some rules of thumbs you can use while defining your network. The next step is to compile the model and then fit the data to the model. And the steps are exactly the same as we have seen in other examples. So basically, we created the model using create model, the code that we showed here, and then we define a batch size. The batch size can be much lower, something like 64 or 32. Those are also good numbers. And the number of epochs here, we have set it to 20. And then we compile. The optimizer is RMS prop. The loss function is categorical underscore cross entropy. And we use that loss function whenever we want to do a classification task. And the metric we are trying to display is accuracy. Now, if you do model.summary, you will see the various layers in the model. Also note how the shape of the output at each step is changing. So we start with a 28 by 28 input layer, and which goes into this convolutional layer, and this one is 28 by 28, and there are 32 filters. And once we apply these filters, the size is 26 by 26 by 32, and there is a reduction in size because the convolutional filter doesn't work on the edges. We have chosen the padding to be the same, and therefore there will be a reduction in size. Next, we see the max pooling layer. The job of the max pooling layer is to reduce the size of the image or the tensor that is passing through, and here it is reducing it to 13 by 13 by half. So dropout layer has no effect on the size because it's simply turning on and off some of the neurons. And you can go over this step by step and see what's going on. At some point, we will see a layer like this. After this dropout layer, we have this shape, which is 1 by 1 by 64. And in this case, we want to flatten this thing before connecting it to a dense layer. So this thing gets flattened using the flatten layer, and then we have two dense layers, and finally we have the output, which is connected to softmax. That is it. Once we have this, we do model.fit, pass it the training data, the training labels, and the batch size, the number of epochs, and we want it to display, so we have turned on verbosity, and the validation set is also set using this line of code. and it trains. We can also plot the accuracy and loss. First, we are plotting the loss here. You can see that the training loss is decreasing nicely. The validation loss is also decreasing nicely. So these are really nice curves when we are looking at a model training. And we can see that the accuracy is shooting up with the number of epochs. So these all look very good. We do not need to do anything fancy here. And you can see the accuracy level has shot up above 90%. I think it is in the 95% range. It is in the 92-93% range. However, if you can keep training and it would have gotten slightly more, slightly better. And this is a very simple network that we had trained. It's nothing fancy, but it still does a very reasonable job. Now, to do inference, we can simply get one of the test data and use model.predict class to predict the class of this. And here it has correctly predicted it to be an ankle boot. We can also move this image up slightly and then send it to the convolutional neural network we have just trained, and it still does a good job. And the reason is that convolutional neural networks are translation invariant to a large extent, and therefore we are able to achieve this result. And finally, we have some exercises for you. Train a neural network on CIFAR10 dataset instead of the FashionMNIST dataset, and see whether you can come up with code that solves the image classification problem. And then train it for an extended period of time, maybe an hour or two, and see how the curves change. Now, if you're using images which are larger in your training set, in that case, you may need to use a GPU to perform this training. The code doesn't change, but you will need to use a GPU-enabled machine, something that has NVIDIA, to do this. You can also use Google Colab if you want to get 12 hours of free GPU service. That is it for this notebook. I hope it was very useful for you. Thank you.